Welcome to Chapter 2, Polynomials. In this lesson we will explore the introduction and types of algebraic expressions known as polynomials. What is a polynomial? A polynomial p of x is an algebraic expression of the form an times x to the power n plus an minus 1 times x to the power n minus 1, and so on, all the way down to a1 times x, plus the constant term a0. Here an minus 1, and so on right down to a0 are real number coefficients. And x is the variable. The highest power of x appearing in this expression is called the degree of the polynomial. Now let us look at the three common types based on degree. A degree 1 polynomial is called a linear polynomial. For example, 2x minus 3 is a linear polynomial with degree 1. A degree 2 polynomial is called a quadratic polynomial. For example, 3x squared plus 5x minus 2 is a quadratic with degree 2. A degree 3 polynomial is called a cubic polynomial. For example, x cubed minus 4x is a cubic polynomial with degree 3. It is important to know which expressions are not polynomials. 1 over x minus 1 involves a negative power of x. The square root of x plus 2 involves a fractional power of x. Neither is allowed in a polynomial. In summary, the degree is the highest power of the variable. Degree 1 is linear. Degree 2 is quadratic, and degree 3 is cubic. No negative or fractional exponents are permitted. Let us now study the zeros of a polynomial. A real number k is called a zero of the polynomial p of x if p of k equals 0. In other words, when we substitute k for x, the polynomial evaluates to 0. Consider the linear polynomial p of x equals 2x plus 3. To find its 0, we set p of k equal to 0. This gives 2k plus 3 equals 0, so k equals negative 3 over 2. Therefore negative 3 over 2 is the 0 of this linear polynomial. In general, the 0 of any linear polynomial x plus b is always equal to negative b over a. Now consider the quadratic polynomial p of x equals x squared minus 3x minus 4. Let us check a few values. P of negative 1 equals 1 plus 3 minus 4, which is 0. So negative 1 is a 0 of this polynomial. P of 4 equals 16 minus 12 minus 4, which is also 0. So 4 is another 0. But P of 2 equals 4 minus 6 minus 4, which equals negative 6, not 0. So 2 is not a 0. Therefore the zeros of this quadratic polynomial are negative 1 and 4. This leads to an important distinction. The value of a polynomial at a point can be any number, positive, negative, or 0. But a 0 of the polynomial is specifically an input value that makes the output exactly equal to 0. These are different concepts, and it is essential to keep them separate in your thinking. Let us explore the geometrical meaning of zeros of a polynomial. We will understand zeros by looking at the graphs of polynomials. First consider the linear polynomial y equals 2x plus 3. When we plot this on a graph we get a straight line. Notice where the line crosses the horizontal x-axis. It intersects the x-axis at the point where x equals negative 3 over 2. This x-coordinate is exactly the 0 of the polynomial. So geometrically, the 0 of a Linear polynomial is the x-coordinate of the point where its graph crosses the x-axis. Now let us look at the quadratic polynomial y equals x squared minus 3x minus 4. Its graph is a U-shaped curve called a parabola. This parabola crosses the x-axis at 2 points x equals -1 and x equals 4. These two x-coordinates are precisely the two zeros of the quadratic polynomial. Notice that in general there are three possible cases for a quadratic parabola and the x-axis. In case 1, the parabola crosses the x-axis at two distinct points and we get two real zeros. In case 2, the parabola just touches the x-axis at exactly one point, which is called a repeated zero or a zero of multiplicity 2. In case 3, the parabola does not touch the x-axis at all and there are no real zeros. Finally, consider a cubic polynomial such as y equals x cubed minus 4x. Its graph is an S-shaped curve and it can cross the x-axis at up to 3 points. In this example, it crosses at x equals -2, x equals 0, and x equals +2, giving 3 zeros. The universal rule is this: the zeros of any polynomial p of x are exactly the x-coordinates of the points where its graph touches or crosses the x-axis. A polynomial of degree n has at most n zeros. We will now study the important relationship between the zeros and coefficients of a quadratic polynomial. This relationship is one of the most powerful tools in this chapter, allowing us to solve many problems without finding the zeros explicitly. Consider the general quadratic polynomial p of x equals ax squared plus bx plus c, where a, b, and c are real number coefficients and are is not equal to 0. Suppose alpha and beta are the two zeros of this polynomial. Then the following two fundamental relationships hold between the zeros and the coefficients. The first relationship is for the sum of the zeros. Alpha plus beta equals -b divided by a. In other words, the sum of the zeros is equal to the negative of the coefficient of x divided by the leading coefficient. The second relationship is for the product of the zeros. Alpha times beta equals c divided by a. That is, the product of the zeros equals the constant term divided by the leading coefficient. Let us verify these with an example. Take the polynomial x squared minus 7x plus 10. Here a equals 1, b equals -7, and c equals 10. The zeros of this polynomial are 2 and 5. Check the sum. 2 plus 5 equals 7, and -b over a equals 7 over 1 equals 7. The sum matches. Check the product. 2 times 5 equals 10, and c over a equals 10 over 1 equals 10. The product also matches. These relationships are derived from the factored form. If alpha and beta are zeros, then p of x equals a times x minus alpha times x minus beta. Expanding this product and comparing coefficients gives us both formulas. Memorize them well, they appear in almost every problem in this chapter.